Now let's look at number 19. Problem number 19 says that one end of a uniform 4-meter long rod of weight Fg is supported by a cable. The other end rests against the wall, where it is held by friction. As shown in figure 12.19, the coefficient of static friction between the wall and the rod is mu static equals to 0.5. Determine the minimum distance x from point A at which an additional object, also with the same weight Fg, can be hanged without causing the rod to slip at point A. And the diagram's right here. Make sure you have a tension right here that this cable is applying to this rod. And that's the sum of forces in the y direction. You have a tension, the y component of the tension. This is the friction force that the wall is applying to this rod. And now you have the gravitational force of this rod, and there's actually another object hanging down here, and that's add a additional force to this rod. And this is the force, the sum of forces in x direction. To the right, you have the normal force that the wall is applying to this rod. To the left, you have the x component of the t, which is the tension. And now let's write this all out. So, frictional force is mu static times Fn. And the mu is given to us as 0.5, so 0.5 Fn. And the sum of forces in x direction is 0 because it's not moving at this point. And that would be m minus t cosine 37 is 0. That's Fn. And we know that Fn is t cosine 37, which is also about 0.8 t. And since the normal force is 0.8 t, the friction would be 0.5 times 0.8 t, which is 0.4 t. Now let's do the sum of forces in y direction. Fy, the sum of forces is equal to 0 because it's at equilibrium point, and friction plus t sine 37 minus 2 Fg. The one Fg is from rod, the other one is from the additional object. And that's 0. So after solving this, we would get so we already find the friction to be 0.4 t right here. So now let's substitute that in, 0.4 t plus t sine 37, which is about 0.6 t, minus 2 Fg equals 0. And after solving for that, we would find tension is approximately 2 Fg. And now we can go ahead and do the sum of all torques. So yes, so sum of all torques at this point at the problem is asking us to find the equilibrium point, so the sum of torques should be 0. And the sum of torques is the torques of the object, which is Fg times x, which is the distance we're trying to find, minus Fg 2.0, which is the torque applying by the gravitational force of the rod, and 2 Fg sine 37, which is the torque applied to the rod by the y component of the tension. 4.0, because that's the length of the distance that is applied by the torque, and that equals to 0. So after we substitute that in, we would find negative fg x equals to 2fg plus 0.8 fg, and the x would therefore becomes 2.8 meters, about 2.8 meters. The solution says it's 2.82, but if you round it, it's actually 2.8, and that's so the minimum distance to keep the rod in equilibrium is 0.8 meters. Alright, so that'll be it.